So we're moving from, we were kind of dabbling in 2 or 3 dimensions for now. We're moving, let's consider what happens if I have 3 or more dimensions. And there's a number of solutions that we're going to go through for the rest of the lecture. So solution number one, what if I have 3 dimensions? Why not use 3-dimensional data? Well, for the most part, our computers are not 3D and our vision is not really, it's more like 2.5D. Things that are far away, we don't really see perspective unless they start moving. But if they're fixed, it's going to be hard to say if you see a dot, does it mean you have a big bird that's sitting 200 feet away from you? Or it's a big mosquito that's sitting right in front of your eye, 1 inch from your eye. So it's kind of hard for our visual system to detect that. And that's the problem with representing it in 3D. So first of all, monitors are not too good. Second, even our visual system, even if monitors would really do a perfect job, we are not that tuned in to 3D. Plus, some people have different defects with you can only see from one eye. That's one problem. But even if people who cannot see in one eye, they still see perceived depth. Why? Because of the parallax. They move a little bit, or the environment moves a little bit, and you can perceive the relative motion. But without any motion, the data is going to be confusing. So here's an example just looking at C, where I can pick any of them, A. And the idea is is A really close to me or is it far away? So if A is hitting this axis right here, then it's really close to this plane. However, if A is really close to me, so that means it's hitting here, that means it's a lot higher. So it's a different way. I have to interpret it in a different way. So that is the main problem with these things. You cannot really tell how far away they are. The other thing is, are really C and B close together? You don't know. They are close together the way we look at them, but one of them may be really close to me and the other may be really far away. So they can still be far on that direction. And one of them can be smaller, the other one can be bigger, so they appear in this picture about the same size. So that's the problem. How do you estimate in 3D? How do you compare individual dimensions? So for the most part, 3D is not that great to represent 3-dimensional data. Just like one dimension was not, unless you do something else, it's not going to be that great with one-dimensional data. And here is a better example of 3D. There are 3 dimensions. So let's say this is a bicycle manufacturer, and they kind of look at defects. So the size is one data dimension, and that's the defects, the size of each circle. So there's a lot of defects here, few defects here, and no defects in this area. So that's one. The other 2 dimensions are obviously shown on axis. And that's a much better way of representing 3D than try to kind of move it around, especially move it around in 3-dimensional, simulate 3D virtual reality. The other thing interesting about this, and I have a 3-dimensional picture of this late in the next set of slides, I think. I'm not going to spend much time on that. I'm just going to point you back to here. So these are the bicycles in production. What can you see here? Somebody went on vacation. And all the bicycles they made there, they were faulty. You can kind of see patterns. So there's a lot of patterns that kind of start to be more available, which you may not be able to see necessarily in a 3-dimensional representation, just the way kind of things move around. Here is another big pattern that obviously what you can see here, these bicycles, something tends to fail about 2 months in production. So if you were to set the warranty for them, you should set them at 90 days. So you don't get to 120. If you want to save money. I'm just being mean. Here's another pattern. What this does, so there were a lot of bicycles produced in May, and after 2 months, that would be July, they failed. Um, Bicycles produced in March failed after 4 months. So 4 months from March is still July. And if you follow this whole thing is July. They failed in July, no matter when they were built. So something must have happened. I know it snowed in July on the bicycle, or it rained too much, and it caused a failure on those bicycles. So it's not necessarily the production, but it's some that happen outside of the environment. So some of these things kind of give you more information than just individual points. FYI, it's kind of a little bit going back to Tufte's multifunctioning graphical elements. They kind of work together to give you, the pattern has a meaning. They work together to highlight a pattern. That's another three-dimensional data that used to have a video. I still have it, but it's just too old to show it. I'm not going to waste time on it. The dimensions here are, this is an electrical circuit. So that one dimension, I guess it's the component where you're measuring. The other dimension is going to be the frequency. So you put something like a sound through this circuit, it will resonate. And the circle tells you if there's a lot of resonance. And I think big circles mean that there's a danger for those components to heat up. There's too much resonance in there. In this case, why do I have it? It's still three-dimensional data, but the only way to look through the entire data set is for this cursor to move. And there's two ways you can make it move. You can animate it, so it'll go up and down. I think that's what this video is doing. Or you can have the user move with, I don't know, with the mouse or with the cursor, move it up and down and go through all the frequencies. So one of the data dimensions is not showing all the time. You have to use it. It's at any point in time, you're only showing one data value for it. You have to kind of explore it somehow, navigate through it, either automatically or manually. If I have more than two dimensions, here is another thing I can do. Project multidimensional data into 2 dimensions. Most of the time, that's what we want to do. So there are 2 ways, self-organizing maps. I think we've seen one when we looked at, in lecture 1, where we looked at mountains, and you had Charles de Gaulle talking about China, and that lecture 1, kind of what CNN was talking in for a year, was using a self-organizing map. That's the, here's a different example. You can see that it actually looks like a map. There are islands, things that don't really have a lot in common with other things. They tend to be isolated in islands. How these SOMs work is they actually run a neural network. And many times, just the way neural networks run, and probably even parameter settings, which is part of the neural network, but you run it twice, you might get slightly different results. So the map can organize different ways. The other, talking about neural networks, the other very popular, another very popular technique in the AI neural network community is this T-SNE. That's what it stands for. It's T, and then people, they don't say T distributed stochastic neighbor embedding. It's T-SNE. And with T-SNE, it's a way to take multidimensional data. It doesn't have 3 dimensions. It can be 100 dimensions. And you project it into a 2-dimensional plane. The projection doesn't work like a real, like you do with 3D, where you point. I mean, this kind of 3D. We're still seeing a projection. So if you look at this plane, it is a projection of the points, because we don't see the 3D part there. But because the neighborhood part and the stochastic, meaning that the projection varies from neighborhood to neighborhood. They try to create something that kind of has the same density per inch, if you want, or per pixel, or per 100 pixels in the projection. So it changes stochastically, meaning more or less randomly, how those things are projected. And I have a good article. Somebody found it. It unfortunately was not an article. It wasn't peer-reviewed and it wasn't published, but it's a website that talks about it. It's a pretty good idea. So let's look at the t-SNE again. If you're doing anything with AI, it seems to be uh, very popular in the AI community. Somehow they don't like self-organizing maps, but they like t-SNE. So I'm just going to pull this up and share my screen. So how to use t-SNE effectively? You can see here is just a square grid with equal spacing. And you can see kind of the steps and how they're trying to project. It's already 2D. So an ideal thing would show up 2D, but the t-SNE sometimes kind of breaks apart, because it applies different transformation in different parts. So in this part of the image, the green one, kind of light green, it applied something. In the blue part of the image, the rest of it applies something else. So if I reset it, and like I said, it's stochastic, so it might actually break it down in a different way. Every time I do something, it will break it down a different way. And the perplexity is something, this is point per side is how many points I have on each side here. So the perplexity is kind of, there's two parameters to consider. One is the number of steps, but after a while you see it kind of sticks, which it's not true always. It might actually, you may run it for more steps and at some point it kind of diverges a little bit. And the perplexity, which they kind of try to explain in this article, is how many it's how loosely balanced attention between local and global aspects. So should you look at a global picture and kind of try and process them about the same, or should you be more focused on the local neighborhood and try and process it? Another way they say here, it's the parameter is a guess about the number of close neighbors each point has. So even with this, if I change the perplexity, and 10 is not a good perplexity, they can will get different shapes. It's doing a little bit better. It still kind of smooshes it on the edges. And here, let's do another one that's completely way off there. So it's smooshes them even more. Well, actually looks pretty good now. So for this example, that perplexity works well. I think the authors of t-SNE, they say between 5 and 50 are good things. So if you ever use that, there are some parameters you have to be aware of. So they will change how visualization looks. So let's try it again with the low perplexity. It tends to break it more. It says a point doesn't have that many neighbors, so it kind of tries to break it down into bigger, more groups, if you want. And here is an example where they took two clusters. They're still randomly generated, but they're about the same. They have the same number of points. And then you can see different perplexities, how they kind of start to look like. If it's too much, they start to get smushed together, one inside the other. If it's too little, they kind of get broken down. And you can see that 30 and 50, something between 5 and 50, like they said, works pretty well in this example. The other thing they do, they look at iterations. They keep the same perplexity, but they move iteration. Again, the same idea. So after 1,000 iterations, you can see it for yourself. Here they say sizes in a t-SNE plot means nothing. And by size, think about the bounding box. So this cluster, the blue one, may have 20 points inside of it. The orange cluster has 20 points inside of it. It's just the density is a lot higher. They're closer to each other. And again, because this thing looks at neighborhoods and it treats them differently, most of the time you would end up with about the same size clusters. So the original size, the bounding box for the cluster, even if it was closely packed, it will tend to kind of spread it out. And the ones that weren't closely packed, that were sparse cluster, tends to kind of crush them together more. And that's what you see there. Distances between clusters mean nothing. Here's the perplexity that you can see how the original clusters look like. So the green one is further away from the others, but that's not the case all the time. For different perplexities, they kind of see different things. So if they add more points, it doesn't do it. Look, this one is almost completely equally spaced if they add more points to the cluster. So on this one, no perplexity gives any meaningful representation. Of the distance, you don't see that the green one, in reality, the green one is further away from the others. And if this were a multidimensional space, you won't be able to tell that immediately. But the projection would not give you that. So this is random noise, and they're basically saying, I think you can see some patterns in here, but they were generated randomly. So it's kind of weird that something that's random may show up as a pattern in the visualization, but that's what t-SNE does. In a way, it tries to find patterns by applying different functions to different neighborhoods. So you can see some of the shapes sometimes, but not always. So shapes also might show up or not. They're not meaningful. Here are shapes. So you can see for some perplexities, they kind of get together, but for others in the middle, they tend to get squashed. The topology, you have there's the cluster in the middle of another, so it's kind of hard to say for a while. You kind of have to look at it before you figure it out. And here's another topology. This is probably a three-dimensional plane. You have one circle in the z x-axis and one circle in the xy axis. But when they show up, they don't show up that great. Here is kind of more of the same idea, how that gets projected. And that's pretty much it. So if you're using t-SNE, be aware. Density and size may not matter that much, because that's the whole idea of the algorithm. It processes neighborhoods differently, and it tries to look at different, like the name of the technique says, it's a stochastic neighbor, and they try to embed neighbors. Next, since I'm here, I'm not going to go back. There is one slide that I don't have in order. So let's talk a little bit about linked histograms. I will let the author of the book is the one who originally built this idea. It's almost like Easy Chooser, but the bars are actually histograms. They're standing up instead of being on their side, flipped horizontal. They're vertical. And so I'll play the videos. There's a demo. You can download the software and run it. It's a Java application I found. The author at some point worked with IBM Research, and they published their Java code. You can load your own data in there and just play with the with attribute. The name of the tool is Attribute Explorer, but it's really a bunch of histograms that are linked by brushing. So that's why sometimes I call them linked histograms, sometimes I may call them Attribute Explorer in the quiz.